Hello guys. Since I was asking you to go over chapter 3 on your own from the book, I'm going to provide a video on examples from chapter 3, and if you like to watch the video, you can watch these examples. So my first example is from section 3.1, where we talk about vectors and how to operate with components. So I kind of prepared that example already written, so we are going to go very quickly over it, but all other examples I'm going to solve. So imagine that we are given two 4 components vector. Vector v, which is going to have components 1, 3, minus 1, and 4. And vector u, which is going to have components 0, 4, 5, and 1. And somebody is asking us, please calculate the next vector. You can label it as vector c, for example, vector c. And that's a 6 vectors v minus 3 vectors u. How do we calculate this? Well, we're supposed to, by the rule of multiplication vector by a scalar, write down scalar in front of the vector and then minus and the second scalar in front of the second vector. And after that, just do the arithmetic on the components. So how do we multiply 6 by a vector of 4 components? We multiply 6 by every component. It's very, very similar to matrix multiplication. 3 by 4 components, also every component by 3. I'm going to write down the result of multiplication, and since we are going to have as a result 2 vectors subtracted, I'm going to subtract components of my second vector from components of my first vector, and that's going to be 6 minus 3. So 6 multiplied by 1 minus 3 multiplied by 0. And then 6 multiplied by 3 minus 3 multiplied by 4. 6 multiplied by negative 1 minus 3 multiplied by 5. And 6 multiplied by 4, which is this 4, minus 3 multiplied by 1. And after that, just calculate the numbers, do addition, and that's going to be the result. Okay? So not very complicated. Let's move to our second example. Second example, create a parallel vector to vector w also. Vector given with 4 components, 7, 2, minus 1, 3, and I want any parallel vector. You know that vectors are parallel if they are different by a scalar coefficient, proportional to each other, right? So how do we create a parallel vector? We are going to just multiply our given vector by some number, and you can choose this number. For example, I'm choosing number minus 5. And the resulting vector is going to be parallel to ours. So what I'm going to do, minus 5 multiply by 7, 2, minus 1, 3. And you basically multiply every component. So we have minus 35, right? Minus 5 by 2 is minus 10. Minus 5 by minus 1, 5. And minus 5 by 3, minus 15. So that's going to be the resulting vector. And this vector is parallel to ours. You see, all components of my new vector are proportional to old ones. So kind of the ratio between x components, let's say y components, z components, and like whatever p components are going to be same number, minus 5. Okay? Well, these are only examples from the first section, and we're going to move to section 2. So 3.2, section 3.2, let me scroll it up. Section 3.2, norm dot product and distance. Okay guys, we are going to start with norm. Norm is going to be kind of length of a vector in our like regular understanding. So if you have 2-dimensional or 3-dimensional vector, that's just like how long is our vector. We remember that we draw vector as arrow. So basically norm is like if you take a ruler, measure it from here to here, how many centimeters or meters. But again, this is for 2 and 3 dimensions. For n dimensions, we are going to set up a formula. And the formula is going to be next. You take first component, square it, add the second component, square it, and until you reach the last component, and also going to square it, and then extract a square root out of this sum. That's the definition of a norm. And norm is going to look like absolute value, just 2 bars, right? And, well, I'm going to consider one example of norm, which is going to be like, okay, consider vector v with components 4, minus 3, 0, and 1. What is going to be norm of this vector? Well, according to the formula, norm of this vector is the square root of 4 square plus minus 3 square. Sorry, my minus 3 doesn't look like 3. Plus 0 square plus 1 square. And we just need to extract the square root. Don't forget about this. So 4 square is 16 and minus 3 square is 9. So we are going to have 25. 0 is 0 and 1 is 1. So we are going to get the square root of 26. That's going to be norm. Norm is always either greater than 0 or equal to 0. To be equal to 0, the vector must be out of 0 components, right? Because the construction of the formula is telling us that we can get 0 here only if all components v1, v2, and vn are equal to 0. Okay, so that was about norm. Now, dot product. Dot product. Well, if you have two vectors, vector u with components u1, un, and vector v with components v1, vn, make sure that we have same amount of components. Then dot product between them is going to be just the product of components which are corresponding ones. So you multiply u1 by v1 and then u2 by v2 and until you kind of multiply all of them, un by vn. And when you add all these numbers, you are going to get, of course, a number. So dot product is a scalar. It belongs to real numbers. Okay? I'm going to find dot product between the same vector v I had over here and extra vector u, which I'm just going to arbitrarily pick up. 1, 2, 5, minus 3. Okay? So what is going to be dot product between u and v? Well, we multiply 1 by the first component, which here is 4. 1 by 4 plus 2 by negative 3 plus 0 by 5 and plus 1 by, again, negative 3. My multiplication doesn't look very nice. I'm going to try to erase it. Okay. And what we have is going to be just a regular number. So we have 4, we have minus 6, that's 0, and minus 3. Looks like we have minus 9 plus 4, which is going to be minus 5. Dot product in a difference with norm. Norm is always positive. Dot product can be positive or negative. Can be equal to 0 as well. Okay. Okay, what else do we need to know? Well, also we need to know the definition of a cosine. When you have two vectors in normal 2-3-dimensional space, you can always kind of draw a plane through these two vectors. For 2-dimensional, they're already sitting on the plane. For 3-dimensional, you can always draw a plane through them, right? And on this plane, you can find an angle. Vector u, you can find an angle between them, right? And you can just take a protractor, something looking like this, and measure this angle. Well, what are we going to do when we have n dimensions, like maybe 15? Well, for 15 dimensions, it's going to be really hard to imagine what kind of angle we are going to have. But for 15 dimensions, we can do something like a cosine of that angle. So physically, there is no angle, but we can define actually something with some kind of function, which is going to be cosine of the angle between two vectors. Well, how we are going to define it? Well, we're going to have dot product in numerator and two norms of each vector in denominator, and that's going to be cosine of the angle. So angle itself is not going to make any sense, but cosine will make sense. It's going to be just a number. How do I know that this dot product divided by norms is going to satisfy conditions on cosine? We remember that cosine by absolute value is less or equal than 1, right? Is it going to be? To satisfy these cosine conditions, we covered in section 3.2 Cauchy-Schwarz inequality. Okay, sorry guys, sometimes I press something wrong on my tablet and I turn something what I'm not supposed to turn. Okay, let's continue. So how do we know that this number is going to satisfy this inequality? We have something which we call Cauchy-Schwarz inequality. shorts inequality is going to look next way. Absolute value of dot product, uv, is going to be always less or equal than norm of u multiplied by norm of v. Now, if we divide this statement by norm of u and norm of v, we are going to figure out that the dot product divided by norm of u and v is going to be less or equal than 1 by absolute value, which means that we can define actually this as a cosine. Okay, well, again, cosine here is not going to define any kind of real angle because for like more than 3 dimensions, kind of hard to say what is going to be the angle. Let's calculate a cosine for some vectors. 1, 2, 5, minus 3, and v equals 4, minus 3, 0, 1, 2 vectors. Let's find a cosine between them. Well, first we have dot product. I'm going to just copy vectors and then calculate dot product, okay? I don't want to do like too many steps at once. 4 minus 3, 0, 1. And in denominator, we are going to have a square root of 1 square plus 2 square plus 5 square plus minus 3 squared. Don't forget that minus is also going to be squared. And then 4 squared plus minus 3 squared plus 0 squared and plus 1 squared. Kind of running out of space here, moving over here. Well, let's do dot product. So 1 by 4 is 4, right? 2 by minus 3 is, well, probably I should write down. So 2 by minus 3, minus 6, right? 5 by 0, kind of 0, and minus 3 by 1 is minus 3. So we are going to get minus 5 here in denominator. So what we have, 1 plus 4, which is going to be what, 5, plus 25, 30, and plus 9, which is going to give us 39. And this part is 16 plus what? 9, which is going to be 25, plus 1, 26. Well, I'm just going to write down the result. 39 square root of 26. And that's going to be a cosine of the angle, let's say, between these two vectors. And I don't have a calculator right now under my hand, so but you can just calculate it. For sure, that's going to be number less than 1, because square root of 26 is already like 5 something. So when you divide this 5 by this, it's going to give you a smaller than 1 number. Okay. What else we kind of learn here together with what kind of other questions we can have? Distance. What is distance? Let me set distance. So what are we going to call a distance between two vectors? Let's imagine that we have one vector u and then another vector v. What is going to be distance between these two vectors? Let's connect u and v as another vector d. And the length of this vector, or norm of this vector d, is going to be the distance. Well, you see that vector d is not a sum of vectors u and v. Actually, if you take vector v, u, add vector d, you are going to get vector v, right? So basically d is difference v minus u. Well, what happens when you subtract two vectors? Well, you subtract components, right? So for example, components are going to be v1 minus u1 and vn minus un. Now, if we find a norm of this vector, it's going to be a square root of v1 minus u1 squared and vn minus un squared. So the distance is actually the difference between components. And we have this formula. Remember, for three-dimensional vector, we have x2 minus x1, and so on. Just like label 1 as vector 1 and 1 as vector 2. Okay. Maybe we should find the distance between kind of some vectors. Let's do as example. Let's consider vector u equals 2 minus 2 minus 1, 1. and vector v equals 3, 2, 4, 4. So according to my formula, distance, I'm going to label it as d, but you can write down dist or like any other letter. Distance is always a number and it's always positive, right? Or equal to 0 when actually we have same vector. And we are going to extract the square root. And well, again, because we have squares here, it's not important which vector you subtract from which. You just kind of, if you choose vector v, like the first one, well, keep it the first one everywhere and you're going to be okay. So I'm going to have 3 minus 0 squared plus 2 minus 2 squared plus 4 minus 1 squared plus 4 minus 1 squared. Kind of weird number, but just for practice. So let's kind of have it. So 3 minus 0 is going to produce 9, right? My 2 plus 2 is 4, so kind of 16. This one, 4 plus 1 is going to be 5, 25. And the last one, 4 minus 1 is going to be 3 plus 9. Oh, kind of some number. So what we have? We have 41, 50. Well, I'm getting 59, but maybe there is a mistake somewhere. Okay, I did not calculate it ahead of time. Okay. What else? Well, guys, the next thing we want to review, or kind of maybe give an example. So if somebody gives you a vector, for example, vector u, which is 0, 2, minus 1, 1. How do we find the unit vector in the same direction? So that's vector u. And this vector u is going to have some norm, right? Norm of this vector u is going to be 0 square plus 2 square plus 1. Oh, sorry. Give me a second. Plus minus 1 square and plus 1 square. So we have like, what, 4 plus 1 square root of 6, I guess, right? So that's a length of vector square root of 6 centimeters. How do we find a vector which is in the same direction but has length 1, not like unit vector in the same direction? Well, if you have a vector with length 5 and you want a vector in the same direction with length 1, well, you probably kind of divide this into 5 parts, and one part is going to have length 1. So basically, guys, the idea is that you take a vector. Sorry, guys. So how do we find a unit vector in the same direction? We divide actually the vector. For example, that's a square root of 6. Imagine that it's some number like, actually it's a number between 2 and 3, like let's say 2.5. So we need to divide it in 2.5 parts, and one part is going to be a unit vector. So unit vector has length equals to 1. And what we do, we just take our vector and divide by the length of it. This way we are going to turn like it into a vector of length 1. You can literally just check square each component and you're going to see that the length of the vector is equal to 1. Okay, and we are going to move to our last section, which is going to be section 3.3, orthogonality. So we're going to start with definition here. Definition, vectors u and v. If the dot product between them is equal to 0, then vectors u and v, which belong to Rn space, are called orthogonal. Well, in our simple words, perpendicular to each other. And yes, for 2-3 dimensions, it's literally going to mean that the angle between them is 90 degrees. For more dimensions, it's just going to mean that dot product is equal to 0. So basically, we are defining that vectors are orthogonal in case when dot product is equal to 0. Orthogonal set of vectors. Imagine now that you have several vectors, and each two vectors are orthogonal to each other. For example, consider a set of vectors I, j, and k. Each two are orthogonal. If you multiply vector I by vector j dot product, you are going to get 0. Well, if you don't believe me, let's do it. I is 1, 0, 0, right? And j is 0, 1, 0. And if you do multiplication, you are going to have 1 by 0 plus 0 by 1 and plus 0 by 0, which is going to be 0. So if you check for the rest, like we have 3 pairs of vectors, ij, ik, and jk, and all the pairs are going to be equal to 0. We are going to call this orthogonal set. So orthogonal set has all vectors orthogonal to each other. Okay? Well, what is going to be next? Well, orthogonal vectors don't have to be unit vectors. For example, these ijk vectors, we know that they are unit vectors, but normally orthogonal vectors, they do not have to be unit vectors. Okay, and next example I want to consider, or next definition I want to talk, is projections. Projections. Well, imagine somebody gives us two vectors, u and a. They belong to Rn. Well, can be 2, 3 dimension, can be n dimension. So let's imagine that vector A is going to look like this and vector U is going to look like this. If I draw them from the same point, what I can do, guys, for 2 and 3 dimensions, I can make a perpendicular line from the terminal point of vector U onto vector A. And again, this U and V are just plain 2-dimensional vectors. I'm going to call vector which starts at initial point of both A and U and ends at this like intersection of the orthogonal line, vector W parallel. I'm going to call it a parallel projection. I'm going to call this vector, which starts over here and goes over here, orthogonal projection. To what these projections are parallel and orthogonal? They are parallel and orthogonal to vector A. So this vector is parallel to A and orthogonal projection is orthogonal to A. So we are going to consider them in relation to vector A. And if you look at the triangle we have over here, which consists out of W parallel plus W orthogonal, you are going to see that the sum of these two is just going to be equal to vector U. So vector U can be represented as parallel projection and orthogonal projection if you do have some extra vector A, and these projections are going to be related to vector A. Well, I'm going to write down that W parallel is parallel to A and W orthogonal is orthogonal to A. Well, I have too many same signs, right? Parallel, parallel, orthogonal, orthogonal. Now, the question is how to find them. We are going to start with parallel projection. Parallel projection. Well, guys, what do we need to know? Well, we do know that parallel projection is parallel to vector A, right? What I'm going to do, guys, I'm going to find unit vector in the direction of vector A. And I'm going to multiply it by the length of this projection, by length of parallel projection. How do I find that length? Well, remember you have a formula. Cosine of theta between two vectors, U and A, is going to be norm of U multiplied by norm of A, right? From where you can find actually cosine of theta by norm of U equals U by A dot product divided by A. So what we have over here, it's going to be the length of this projection. Well, because these are just two-dimensional vectors, we're just going to treat it as two-dimensional vectors. So that's a right triangle, right? How do we find this length? We are going to multiply hypotenuse, the length of vector u, by cosine of this angle. We are going to get adjacent side. What's going to be length? So I'm going to copy this into length, and we are going to have a over a multiplied by UA dot product divided over length of A. If I modify this formula a little bit, I'm going to put dot product in front and divided by norm of vector A squared, because I have two of them, right? What I'm going to have, guys, looks like we have lots of like vector A and U, but norm of vector A is just a number. This dot product is also just a number, so that's why I put them in front. The only vector here is this. This is vector. This is number. Okay? So that's how we define like parallel projection, just a formula. How do we find actually orthogonal projection? A second. W orthogonal. How do we find orthogonal? We remember we have U equals parallel projection plus orthogonal projection. From where? Orthogonal projection equals U minus parallel projection. If you do know parallel projection, you just copy the formula. So it's going to be U minus UA divided over norm of A squared multiplied by vector A. That's going to be orthogonal projection. Okay? And we can just kind of calculate it. Let's let's write it down some other way. In the book, guys, they can also use next notation, parallel projection. They're going to call it projection along vector u, along vector A of vector u. For orthogonal projection, they are going to put orthogonal. Vector A along which we use the projection is here, and the main vector which we are projecting is this one. Okay? Well, I'm going to calculate parallel projection for next vectors. I'm going to consider example, and that example is going to be vector u equals 2, minus 1, 3, and vector A is going to be 4, minus 1, 2. So I'm going to find pro of u onto A. I'm going to use the formula. So I'm going to have UA divided by norm of A squared and multiplied by A. Well, let's do it. So 2 minus 1, 3, dot product 4 minus 1, 2 divided by square root of 4 square plus negative 1 square plus 2 square squared, right? And vector A is just a copy of the vector 4 minus 1, 2. Then the only number we need to calculate actually is going to be this one. This one is going to be a number. We're not going to calculate anything here just because that's just a copy of vector A. Well, let's do calculations. So 2 by 4 is 8, right? Minus 1 by minus 1 is 1. 3 by 2 is 6. It looks like 15, right? What do we have in denominator? Well, the square root and the square are going to cancel each other. So probably I'm not going to write down the square root anymore. I'm just going to square each number. 16 plus 1 and plus, I think that was 2, right? Let me double check. Yeah, that's 4. 2 squared is 4. And the vector 4 minus 1, 2. Well, let's add. So I said that that's going to be 15. What do we have in denominator? 16 plus 4. It's 20, so it's 21. And that's 4 minus 1 and 2. Well, I think we can cancel a little bit, like over here from 15 and 21. We can cancel 3, right? So it's 5 over 7. 4 minus 1, 2. What else you can do? You can actually multiply this fraction into every component, and that's going to produce just one vector. Maybe in the homework they're going to do it. To find orthogonal projection, this one, we are just going to take whatever we found over here and subtract it from original vector. So we take it and subtract it from original vector, which I think you can do by yourself. I don't think that you need a video on this. Okay, and that's all from chapter 3. Okay, we are going to finish at this point.